Hello and welcome, class, to the beginning of Chapter 16, wherein we are going to begin discussing what is known as dynamic equilibrium. So, dynamic equilibrium is a concept all wrapped up around the notion that some reactions, in fact, a fair number of reactions, are reversible in nature. In other words, as reactant turns into product, that product, as it starts to build up, will begin to react with itself or decompose reversibly to regenerate reactant. Now, this process of reversible reactions, right, going backwards and forwards, will at some point reach what is known as equilibrium, so a steady state forward and a steady state in reverse. So it appears as though the reaction mixture is no longer changing, even though there is this dynamic reaction constantly happening forwards and backwards. So moving forward throughout this lecture, you may notice that the volume of my voice gets to be a little bit quieter. That is because this is another one of those lectures from last spring, the spring of 2020, that I've kind of tweaked a little bit for this semester, made it more general, more accessible, right? Removed anything specific to last semester in terms of announcements or homework problems and stuff like that. Continuing forward, throughout this lecture, you may need to turn the volume up a little bit, but also, just like the last one, I'm going to remove the lo-fi beats from the background just to make the audio a little bit clearer. All right, so without further ado, let's start talking about dynamic equilibrium in more of a detailed sense. Okay, so reversible reactions. Everything that we had been talking about in the context of complete reactions, right, reactants going from reactant to product 100% of the time, throw it out the window. We're not going to be having those conversations anymore. They were very nice, very convenient, but sadly most of the reactions that we're going to be talking about for the rest of the semester, and in fact most of the reactions that occur in the world period, fall under the umbrella of reversible reactions. These are reactions that go from reactant to product simultaneously. Product is going to be turned back into reactant. So as I have written here, reactants are simultaneously converted into products, which are converted back into reactants, which are ... This process, this cycle of reactant turning into product and product turning back into reactant is constantly happening. So reversible reactions, for that reason, are not complete. There is no limiting reactant, there is no excess reactant, there is no theoretical yield, no percent yield, that we can meaningfully measure based on stoichiometry. Stoic is still going to be useful to us, but not in the complete sense that we have been talking about it thus far. We're going to have to be almost framing the conversation of stoichiometry in this whole new light of reversible reactions. So this generic reaction, as it is listed here, A plus B, is going to be reacting reversibly, hence this back and forth arrow, with C and D. This is going to be one of our new best friends. So we're going to be seeing this generic reaction a lot as a means to describe equilibrium in a more general sense. But before getting into too generic or too general of a conversation, let's lay out an example of a reversible reaction so we can kind of sink our teeth into exactly what it is that we're talking about. And we're going to frame that conversation in terms of reaction rates. So reaction rates we've just finished talking about, right? Chapter 19 was all about reaction rates, the mechanisms, the rate law expressions, integration, time, all of that is still going to be in the back of our heads as we're having this conversation about equilibrium in a chemical sense. So as it is written here, a reversible reaction is at equilibrium, and when we say at equilibrium, what we mean is that the reaction is quote unquote finished. It's not to say that a reaction is finished or at least a reversible reaction is finished when all reactant has turned into product. That is not the case. A reversible reaction is going to be finished when the forward rate is going to equal the reverse rate. And there's one big clue as to when this happens and what it looks like in terms of concentration versus, on this x-axis here, we're going to have time. So when these two rates are equal, when forward rate is equal to reverse rate, the concentration of the reactants in products are going to be constant. We will see no more change in the concentration of reactant and product. So let's look at this concentration versus time plot here, corresponding to the reaction of dinitrogen tetroxide decomposing into 2-nitrogen dioxide. So in this reaction, our quote-unquote reactant our N2O4, we're starting with some certain concentration. It doesn't really matter what it is. We'll just say X molar. And as the reaction progresses, as this N2O4 decomposes, we can see that the concentration of it is going down at a certain steady rate. We can also see that the concentration of the product as the reaction is getting started is increasing, right? We are forming that product. But eventually, what we're going to see as the product is being produced, the reactant is being totally used up, it's being consumed. There's a point, and on this graph it appears to be approximately right here, where the concentration of our NO2 and N2O4 are now constant. Right, we have this steady line horizontally, meaning that concentration now, as a function of time, is no longer changing. This is not to say that our N2O4 is not turning into N2O2, it's just that the rate that this is happening as the reactant is turning into product is the exact same rate with which the product is turning back into reactant. And as a result, we see no meaningful change in the concentration now of the N2O4 or the NO2. We are now looking at a constant steady state. So even though this reaction is still constantly happening, there is a dynamic, meaning that there is change occurring, right? There is movement, there is change. There is a dynamic equilibrium. It's not like the reaction is just totally stopped. It's still ongoing. It is dynamically occurring, but we're going to say that the reaction itself is finished because now there's no change occurring that we can see, no meaningful change. The concentrations now are the same, and they will remain the same forever unless there is some type of disturbance in the system. Okay, so how can we then quantifiably connect concentrations to this new concept of a reversible reaction or a dynamic equilibrium? Well, we're going to use the reaction rates idea again to kind of help us out here, since what we had just defined is that the reaction rate in the forward direction, where here the F stands for forward, of the reaction that we just talked about. This is the same reaction, the N2O4 decomposing into 2NO2 in a reversible manner, hence this double arrow, this back and forth arrow is going to, from now on, signal to us that this reaction is reversible. So as the N2O4 decomposes into the NO2, there's going to be some forward reaction rate, and that rate's going to be equal to the rate constant times the concentration of N2O4. This has been found to be a first order reaction, so there's a little exponent of 1 up here. The rate of the reverse, though, is also going to matter, where this little r is going to stand for reverse. Since this reaction is going forward from reactant to product, but is also going in reverse from product to reactant, there's also going to be some type of reverse rate. And so that reverse rate is going to be equal to the rate constant Kr times the concentration of NO2 squared. And so this reaction rate has been found to be a second order reaction rate, and in this case, there is no coincidence to the fact that there is a stoichiometric coefficient of a 2 here, but we'll be talking more about that in a brief second. For now, let's tie together this last loose end of if your forward reaction rate is equal to your reverse reaction rate at equilibrium, we can also say that our Kf times the concentration of N2O4 is equal to your rate constant Kr times the concentration of NO2 squared. All right, so we're going to set that then up. Our Kf is equal to the N2O4 concentration, or Kf times the N2O4 concentration is equal to our Kr times the NO2 squared concentration. And so what's pretty neat about this, again, the math we're about to do is all at equilibrium here, is that we can see that we have two constants, right? Two numbers that don't change. They are a function of temperature, activation energy, collision factor. They're all kind of the background environmental terms. So let's say we want to pull all of the constants to one side. Our Kf divided by Kr is going to be also equal to the concentration of NO2 squared, all divided by N2O4 concentration. And so if we are at equilibrium, the ratio of the concentration of our products, which again we can see up on top, divided by the concentration of our reactants is going to be constant. And this we represent this type of equilibrium constant with a big capital K. This is going to be an equilibrium constant. And this constant, since if we look over here on the left, is equal to a ratio of these two other constants, which are dependent on things like, again, temperature, activation energy, collision factor A. This is an EA. The equilibrium constant will always be the same constant so long as we are at the same temperature and we are looking at the same reactant. Like if we're not adding any type of catalyst to it, this equilibrium constant will be true for this reaction always. At least always, so long as these variables are not changing. So if we're at the same temperature, if we're looking at the same reaction, again, we're not adding any type of catalyst, this equilibrium constant will always be true. This will always represent the ratio of products to reactants for this given reaction, no matter what. And so from this example, we can draw a couple of conclusions corresponding to our generic reversible reaction. So here we have, again, our A plus B is reacting reversibly to create C and D, and this reaction, again, is running in reverse. The ratio of the product to the reactant, as we had just, rearranged our previous example to be a ratio of product concentration divided by reactant concentration, here we can do the same thing for the generic reaction. The ratio of the product and reactant concentrations is constant at equilibrium. For the exact reasons that we just stated, this ratio of concentration of product divided by concentration of reactant will be equal to the Kf divided by Kr, meaning again that if we're looking at the same temperature, haven't changed the activation energy at all, this ratio will be constant and can be represented by this capital Kc for this reaction always. Okay, so now that we have talked about what an equilibrium expression is, how it is a ratio of products to reactants, here are the rest of the topics that we're going to be introducing throughout the rest of this lecture for the generic concept of equilibrium and the all-encompassing umbrella idea of a reversible reaction. Namely, we're going to figure out how do you write equilibrium expressions for given chemical equations, like how we're going to see some more examples of tying the equation and the Kc, its equilibrium expression, together more tightly. We're going to talk about what the magnitude of Kc means, the ratio of your product to your reactant, is going to tell you something about the overall chemical equation and how the products versus reactants are more stable, or how you're going to have more than one possibly than the other, because equilibrium does not mean that you have equal numbers of product to reactant. Equilibrium means that the rates of your forward is equal to the rates of your reverse, and this is going to be constant throughout the rest of the semester. We're going to talk about how if you manipulate a chemical equation, that's going to change your value of your equilibrium constant. For instance, if you add two reactions together, or if you swap it, like reactants become products, products become reactants, how does its Kc change? And also, what other forms of equilibrium are there? Because we have the equilibrium constant as is dependent on our variable right now, C being concentration. But as we will be discussing today, as well as in the rest of the chapters to come, there are many forms of equilibrium. But regardless as to what type of equilibrium we are working with, this constant, this idea that the rate of the forward reaction is going to be equal to the rate of the reverse reaction will always, again, remain true, meaning that your concentration of products to reactants, or let's say pressures, or etc., like whatever type of equilibrium we're working with, products to reactants will also always remain true. Okay, so let's get some more practice writing out some equilibrium expressions for some given reactions. Since this process is going to be the same process that we're using to write out equilibrium expressions, no matter what the reaction is, let's get some practice. So there are two different types of equilibria, equilibria being the plural of equilibrium, that we can talk about. The first is a homogeneous type of equilibria. This occurs when all of your reactants and your products are in the same phase. So much like a homogeneous catalyst, where the catalyst was in the same phase as the reactants. Here, a homogeneous equilibria is going to be represented when your reactants and products are all in the same phase. So here's a good example of that. We have H2 and Br2 both in aqueous phase, reacting reversibly to create some hydrobromic acid, also aqueous phase. And so the Kc expression for this, I'm definitely going to invite you to pause the video, see if you can't write out the equilibrium expression yourself. First, double check your answer to mine. And my answer is going to then be a Kc. And we're always, again, going to be doing products over reactants, corresponding to how the reaction is written above. Because yes, this reaction is reversible, meaning that your products could have been written as reactants and reactants could have been written as products, but your Kc, your equilibrium constant expression, is always going to correspond to the reaction as it is written. So your reactants, for convention's sake, will still be on the left, and your products, for convention's sake, will still be on the right. And so from this, we can say that our Kc, or equilibrium constant, as is dependent on concentrations. And yes, there is a subscript of a C because there will be other forms of an equilibrium expression that we'll talk about, but we're going to be focusing on concentration first. So this is going to be equal to concentration of products divided by concentration of reactants ratio. So here we have a concentration of our one product being an HBr, and we're going to raise this concentration to the 2, since there is a 2 in front of the HBr. The reactant concentrations are going to be an H2 times a Br2. And since there are only stoichiometric coefficients of 1 in front of the H2 and the Br2, there's going to be a 1 in front of the H2, a 1, or not in front of, a 1 in the exponent of the H2, and a 1 in the exponent of the Br2. And so this is going to be our equilibrium expression as dependent on concentration for, or corresponding to, this reaction above. So once this reaction reaches equilibrium, this ratio of products to reactants then will be true. Heterogeneous equilibria are sort of, the hand-holding partner of the homogeneous. The difference then, again, similar to the catalyst example where the heterogeneous catalyst was in a different phase of the reactants. Here, not all of the reactants and products are going to be in the same phase. Not all of them. So most reactions that we can see and work with in aqueous solution are going to be some type of heterogeneous equilibria. And the key difference here when it comes to writing an equilibrium expression for this type of equation or this type of chemical reaction is that only variable concentrations are going to be included in your equilibrium constant expression. This is not to say that the concentration of anything that is not variable doesn't matter to the reaction rate, but when it comes to looking at ratios of products to reactants, ratios, so the combination of the ratio of these rates, any variable that doesn't change concentration ends up not mattering to the equilibrium constant since it gets canceled out, right? A constant number divided by a constant number becomes 1. And so to make our lives easier, we are not going to include any species that doesn't have a variable concentration. Okay, so what does that mean? A variable concentration means that your phase is going to be aqueous or gaseous. Since in an aqueous solution, we can have varying numbers of moles to volume, right? We can change the concentration here. Or similarly with a gas, according to PV equals nRT, pressure is variable with numbers of moles, right? That was Avogadro's whole shtick, was that you can change the number of moles of a gas that you have and change the pressure, change the volume, change the temperature, etc. as a result. So these two phases are always going to be phases that are going to be included in your equilibrium constant. Phases that are not going to be included, phases that are not variable, are going to be things like liquids and solids. Since liquids and solids have constant densities, right? When we were talking about condensed phases getting into chapter 12, this was one of the things, this factors was what set a liquid and a solid apart from a gas. These things have constant densities, whereas gases have variable densities. So since your liquids and your solids have constant densities, they also have constant concentrations. You can't change them. And so for that reason, even though in this given reaction below, where we have acetic acid interacting in water to create some acetate ion and some hydronium ion, H3O+, the water concentration over the course of the reaction does not change because it is in liquid form. It has a constant density, therefore it has a constant concentration. And so your Kc, your equilibrium expression, is only going to include the products that are in aqueous phase and the reactants that are in aqueous phase. So the products that we are going to include are going to be both of them. We can see both the acetate ion and the hydronium ion are in aqueous phase. Since they're in aqueous phase, they can have varying concentrations. The CH3COO minus concentration will be multiplied by your H3O plus concentration, and all of this will be divided by the acetic acid CH3COOH concentration. It should be 1C. Okay, so thus far we have two big rules when it comes to writing our equilibrium expressions. The first rule is that we're always going to be looking at products over reactants. Always, every time. Our second rule is that if a species apostrophe, if that species is not in some type of variable concentration form, in other words, liquids or solids, we are not going to include them in our equilibrium constant expression. Because the concentrations don't change, there's no reason to include this in a ratio of concentrations because it's always going to be constant. It will always cancel out when we are comparing equilibrium constants. Okay, so let's talk about the magnitude of your equilibrium constant. What does it signify? What does the number mean? Now, we are going to be looking at some specific examples to see what these types of numbers look like, but before laying out any specific example, let's look at what the numbers could qualifiably mean, and then we'll put them in a context. So the magnitude of your equilibrium constant is going to signify how complete versus how reversible a reaction is. So in the case where your equilibrium constant, or the ratio of product to reactant, is going to be huge, significantly greater than 1,000. That's what this means. If your equilibrium constant is super, super big, like bigger than a ratio of 1,000, what that means is, if we look at our equilibrium constant expression, like the most generic form of it, where we have products being multiplied in the numerator, we have, numerically speaking, a ton of product. A ton of product to make this first situation true, right? If our equilibrium constant numerically is a very big number, that must mean that we have a very big numerator. So this first scenario, this first situation, is going to represent a complete reaction in the forward direction. In other words, all of the reactions that we have been talking about up until this point, all of our complete reactions, if we were to work out the math, would have equilibrium constants that are significantly larger than 1,000. These are going to be reactions that are very, very complete, that have very, very little reactant and a ton of product. The other situation that we have talked about, like in a non-spontaneous reaction, or a reaction that just doesn't move forward on its own, is going to be laid out in this second situation here. So if your equilibrium constant is much, much smaller than 1,000th, right, this 10 to the negative 3 means that your Kc is going to be very small. And if it's very small, algebraically speaking, if we come back over to our generic expression, that must mean that our denominator in this case is going to be very big. So in other words, if we're working in the situation where we mix two species together and we have a ton of reactant still sitting in the beaker, what this tells us is that there was no reaction. Nothing happened. However, What this also signals is that if we were to have mixed the products together, more than likely we would have ended up with a forward reaction. In other words, if our Kc is very, very small, meaning that at equilibrium we have a ton of reactants, the reverse reaction will be complete. Okay, so far we've kind of linked the equilibrium expression, this idea of the ratio of products to reactants, to the previous situations that we have talked about, either a reaction being complete in the forward direction, or in the instances that we have witnessed no reaction in the forward direction, what this really means is that the reverse reaction will be complete. And this is signaled by a very, very small equilibrium constant. So the situations that we are going to be getting ourselves into now, the most commonly, are going to be those where our equilibrium constant is going to be somewhere in between these two extremes. So our equilibrium constant is not going to be incredibly tiny, it's not going to be incredibly big. It's kind of like a Goldilocks situation where in between we are working with true dynamic equilibria. We are working with true reversible reactions. Reactions where it's going to matter whatever this equilibrium constant is. And this equilibrium constant will tell us a little bit about the nature of the reaction, since we are going to have a meaningful concentration of both reactants and products. Okay, so let's look at this equilibrium expression example. So we have a given reaction here. Again, we're going back to our N2O4 reaction. And it's going to be decomposing into the 2N2 or NO2s. So this reaction is going to be moving back and forth. So we can use the concept of our equilibrium expression, which we've already written for this reaction, right? The concentration of our product, NO2, up into the, or is squared, this stoichiometric coefficient being raised into the exponent, and the other concentration of our reactant, the N2O4, is going to be in the denominator here, right? Ratio of products to reactants at equilibrium will be constant for this reaction, following the graph that we had already witnessed where the concentration sort of leveled out. So let's say we're looking at a trial 1 versus trial 2 situation. What we want to do is use trial 1 to calculate numerically what Kc is going to be equal to. Then in trial 2, where we have the Kc, we can use it to find a missing concentration when the reaction is at equilibrium. And that is going to be the crux of this type of problem that we are introducing here. We need to be at equilibrium in order to just straight up use this equation as we are going to be using it. So that's the big assumption. We are assuming, as is labeled with these concentrations here, that we are at equilibrium, that the reaction now has reached a steady state where reactants and products are moving backwards and forwards at the same rate. Okay, so the way that we can use this equation is we can take the concentrations numerically that we have recorded here at equilibrium and insert them into our equilibrium expression here. So the concentration of our NO2, we can see here, is a 0.0547 molarity squared. Squared coming from this square up here. Gonna make sure that we don't lose that squared because it will definitely affect our math in some way. The concentration of our N2O4 at equilibrium, we can see here, is a 0.643 molar. Okay, so here I'm going to bite my tongue a little bit because I harp on units a lot. Units tell us a lot about a chemical equation, about a mathematic equation, how everything kind of links together. We've been following the units, quote unquote, this entire semester. Now I'm here to tell you that in any conversation we have about equilibrium, setting up an equilibrium constant like so, the units don't matter. In other words, there is no one big unit for the equilibrium constant. It's going to depend completely on the reaction that you're working with. And so for that reason, since it's so tied directly to the reaction that you're working with, and it doesn't really give you a lot of useful information, we are no longer going to be including units in this type of problem. So in other words, we're going to be taking 0.0547 squared, dividing it by this 0.643, and this is going to give us a value that is equal to 4.65 times 10 to the negative 3. And there is no unit here. This is going to be a unitless ratio. And that's the biggest reason as to why we are going to be dropping these units, is because it's all about ratios. We're all working in the same unit here, the same units in the numerator as the denominator. The specific number of the units that we have doesn't matter. It's all a ratio of concentration. And so this value is going to be unitless. I only ask that you do not forget that this is a unitless value because we're looking at ratios of concentration units here. And so we're going to say that they, quote unquote, cancel out. Even if they don't quite cancel out, for informational sake, they cancel out. This could be a little bit of a problem for anyone who has been following the units, who's gotten into that habit, and now you're suddenly unitless when it comes to this type of problem. Just don't forget the context of what you're working with. It's all about the ratios of concentrations. If you remember that, you will still be fine. Okay, so we've just found that the Kc for this given reaction at a constant temperature is going to be 4.65 times 10 to the negative 3. This is going to be true no matter what trial we are working with. So long as the temperature is the same, this Kc is going to be the same. Meaning that the ratio here of products to reactants, again, so long as we are at equilibrium, will be true no matter what the concentration of our product to reactant is going to be. 0.378 is now this new concentration in trial 2. We don't know what the concentration is of the product, but given that this reaction has reached equilibrium, as we are being told by these little subscripts of an EQ here, we can use our equilibrium constant to rearrange and solve for the concentration of NO2. So the way that we can mathematically do this, let's get rid of this, because we are going to be working with square roots, cubed roots, all types of roots. The way to rearrange and solve for this Kc then is going to be concentration of NO2 is going to be equal to the square root of the concentration of the N2O4, that's 0.378, times the value of our Kc. For the sake of space, I'm just going to write Kc, but this whole value, the 4.65 times 10 to the negative 3, is going to be right here. We're going to square root all of that. This is going to give us a concentration for the NO2 that is equal to 0.0419. And this will have a molar now return back, since it is a concentration in the units of molar. Okay, so let's take a quick beat before moving forward to make sure that this value actually makes sense. So in trial 1, the ratio of product to reactant, we can see that the product concentration was a 0.0547, and the reactant concentration was a 0.643. Well, between trials 1 and 2, we can see that the concentration of the reactant decreased. What this means is that the concentration of our product must also, let's see, I'm going to write this sideways, decrease between trials 1 and 2. This is because we still want that ratio of product to reactant to be the same. Well, if your reactant decreases, then your product must also decrease to keep this ratio mathematically equivalent. So that's going to be a double check for us. We're always going to be looking at what is the ratio of products to reactants here. And does the answer that we're calculating line up with that consistent ratio of products to reactants? All right, but with that, we are going to call it a chapter. So here we have some section review problems out of chapter 16, all kind of focused around understanding the equilibrium constant just in the most general sense. As the chapter continues, we'll be seeing a variety of ways with which this equilibrium constant can be used, either along with initial concentrations to predict equilibrium concentrations or to predict changes, the directionality of the reversible reaction. So there are a lot of different ways that we can use this, and again, for the most part, for the rest of the semester, we're going to be focusing on using the equilibrium constant to be able to understand these more complicated systems. All right, but if you have any questions, please do not hesitate to leave me a comment below or shoot me an email if you're in my class. If you have homework that is due, please double check and do your homework. And until next time, class is dismissed.